on this set of notes, I've combined several sections here because all of them are relating to polynomials, so it makes sense to me to do all of the stuff about polynomials together. So a lot of this is review, so I'm going to go through it pretty quickly. Reminder of long division and synthetic division. So if we wanted to divide these polynomials, we would set it up like a long division problem with numbers. And then just like when you're dividing with numbers and not polynomials, you think x minus 4 times what gives me this first term here, which is 6x squared. So that would be x times 6x. So I multiply by 6x. 6x times x is 6x squared. 6x times negative 4 is negative 20x. And then I subtract. Don't forget to subtract the whole thing. That's 0. And this would be plus 20, so this would be negative that was 24. Negative 2x, and then bring down the 12. And then we think x times what gives me negative 2x, and that's negative 2. Negative 2 times x is negative 2x. Negative 2 times 4 is plus 8. And then we subtract. Don't forget to subtract the whole thing, so 12 minus 8 is 4. So the quotient, remember quotient is the answer to a division problem, is 6x minus 2, and the remainder is 4, so we would put 4 over the divisor, which is x minus 4. If the remainder was 0, then we wouldn't have that term. And then reminder of long division. If your divisor is linear and it's of the form x minus a number, if you have a coefficient here, it won't work. So you put the root that corresponds to the factor. So not the negative 4, but the 0 or the root that goes with it, which is 4. And then the coefficients of this polynomial along the top. So it would be 6, negative 26, 12. And if you had a missing term, there isn't one here, but we have x squared, x, and constant. If you were missing one, you'd need a 0 in that place, or you'd get the wrong answer. Bring down the 6, and then you multiply 4 times 6 is 24. And then you're always adding here. Negative 26 plus 24, and then 4 times negative 2 is negative 8, and then you add, and you get 4. So this is your quotient, and the quotient is always going to be a polynomial of degree 1 less than the one you started with. So instead of x squared being the first term, x would be the first term. So it would be 6x minus 2. And then this is the remainder, 4 over the divisor, which is x minus 4. And it was the same problem, so we should get the same answer. Okay, a couple of theorems here. If you have a polynomial and you divide it by a linear factor, then the remainder is the value p of c. So we're going to use that theorem down here. And then we have the factor theorem. So if you have c, a 0, which means x-intercept, right, of a polynomial, if and only if x minus c is a factor. That's kind of obvious, I think. Like, if that's the factor, then that gives you the 0. Okay, so we're going to take this long polynomial, find the quotient and remainder, and then use the remainder theorem to find the polynomial evaluated at 2. So the first thing we need to do is divide by x plus 2. So I'm going to do that using synthetic division. And actually, I'm going to do it speedy quick by just showing you my work here. So you can pause if you need to catch up. So coefficients of this polynomial, and there had to be a 0 there because the x squared term was missing, so that's important. And then the 0 that corresponds to this factor is negative 2, and then we do the process. So that's the remainder, okay? So we get this polynomial that's 1 degree less than the one we started with these coefficients, and then this is the remainder, so it's 1 over the divisor, which is x plus 2. Again, reminder, the remainder is 1. So if we use the remainder theorem, we divided this polynomial by x plus 2. So the remainder, which is 1, is the value p of c, so p of negative 2 is 1. So you can check that on your calculator. So that's a pretty useful fact. I'm actually going to keep going like this. So let's show that p of 1 equals 0, and then use the result to factor this. So we could easily show that p of 1 equals 0 by plugging 1 in here. So if we plug 1 in and we work it out, we do in fact get 0. So that tells us that, using the remainder theorem, x minus 1 is a factor of the polynomial. So now we know that we can factor x minus 1 out. So if we do that using synthetic division, so the 0 that corresponds is 1, these are the coefficients of the polynomial. We do synthetic division, the remainder is 0, that means it was a factor, so that's good, our process worked. And the result is 1 degree less, so quadratic, so x squared plus x minus 6, and then that factors relatively straightforward. But we were actually trying to factor the original cubic, so we get these two factors and the one we factored out initially, which was x minus 1. So this is fully factored cubic. All right, next example. We're going to find a polynomial that has degree 4, and it has these 4 zeros, and then an extra condition that the coefficient on the x cubed term is negative 6. So it's relatively straightforward to do this. We're just going to write 4 factors that correspond to each of those zeros. So x plus 3 times x, because that would be x minus 0, x minus 1, x minus 5. And then if we multiplied this out, which you don't have to because the directions didn't say to put it in standard form, so don't make extra work, your leading coefficient would be 1x times 1x times 1x times 1x. So your leading coefficient would be 1x to the 4th, and we want our leading coefficient to be negative 6. So if we multiply the entire polynomial by negative 6, we would get negative 6 times 1x to the 4th, so that would be our leading coefficient. And we don't need to multiply it out. All right. This rational root theorem you definitely learned in Algebra 2, so this is a review. So remember, if you can't factor it by other methods, you can make a list of all the possible rational roots where p and q are integers, and p are factors of the constant term, and q are factors of the leading coefficient. If it was me, I would have done alphabetical order, but I wasn't the one who decided to name these this way. So we're going to list all the factors of the constant term, plus or minus 1, plus or minus 3, plus or minus 9, and all the factors of the leading coefficient, so plus or minus 1, plus or minus 2. And then we want a list of all the factors of p over q. So here's the list, so don't forget the fractions. You've got to do the 9 over 2 and the 3 over 2. So a lot of things to try. So let's try one. So let's just try negative 1. So we put all these coefficients across the top. There wasn't a missing term. And then we do synthetic division, and lo and behold, it worked. So that means that our new polynomial of degree 4 has these coefficients. But I don't actually need to rewrite it as a polynomial yet. I can just try factors of the new polynomial and just plunk these coefficients into another synthetic division box. And I'm still going to pull numbers from this list, although my new polynomial could have new combinations. It doesn't, because it has the same coefficients here, but it might have different ones. And you might get a smaller list. You won't get a bigger list because it still had to be factors of the original. So if we try negative 3, lo and behold, that worked. And then we're left with a quadratic, which factors. So remember, the goal was to factor the entire quintic polynomial, so we should have 5 factors. So what do we have? We had x minus 1. I don't think that's right. I'll go back and check. So we had x minus 1. Oh, I think I skipped one. I accidentally started with that and not this. So my bad, but you see the process. So I actually tried 1 first, and then this new polynomial went over here. Anyway, so I got x minus 1, x plus 1. Notice that the factor has the opposite sign of the 0. And then x plus 3, and then 2x minus 3. And then I had x plus 1 again. Whoopsie. So this one's squared and not that one. All right, good, we caught my mistakes. And that's a good place to stop.